Swayam Prabha. Digital India. Educated India.
I thought I would start by just telling you a little bit about myself. I know that we're going to get acquainted a lot this week, but I thought I would say a few words about, but although Ilax already, no, it's here, sorry. Yeah, said a few things, but just to set the stage. So I'm from the University of Lyon, which is sort of central east of France. And in the university, I'm from a lab called the Institute of Light and Matter, because there's a lot of spectroscopy physics done in my lab. And in that lab, I coordinate a research group that focuses, as Ilak said, focuses on modeling crystalline defects, so the topic of this week. Just to give you a very quick overview, we study materials from the atomic scale to the macroscopic scale, going through the mesoscale here. So we do a lot of molecular dynamics simulations up here. We do a lot of DFT calculations down there. Then we try to pass on the information here to dislocation dynamics at the mesoscale. Or also to look at plasticity in amorphous systems. And then we have some activities at the macro scale, more using discrete element simulations to look at fibrous systems, and some fun things about crowd dynamics. So this week, what I'm going to do is mostly talk about what is happening at the atomic scale and how we can model different types of defects, whether they are dislocations, as shown here, or interfaces shown here or there, or looking in more details at the core of dislocations. So the organization of the course will be, so I'm going to talk in the morning. I don't know how long it's going to last every morning. We'll see how it goes. I have prepared slides that you can access. You got the link, I guess, through the WhatsApp, and I'm going to show it again on the next slide. So this does not apply. Sorry, this is not true. Everything is online. As you will see, I like to ask questions and try to get the students engaged. So please, if you have questions, reactions, comments, ideas, if you know things that I don't, because I don't know what your backgrounds are, but I'm far from knowing everything. If I say something wrong, or if you have something you want to add to what I just said, please feel free to speak. Any intervention will always be welcome. So this is for the morning, and then the afternoons we have these tutorials. So I've prepared tutorials using, so for those who have already done atomistic simulations, we're going to use LAMPS for the molecular dynamic simulations. Ovito to look at the configurations, and Atomscape to create the initial configurations. But we'll talk more about that starting this afternoon. What else did I want to say? Yes, so I guess you have this link where you can get the lecture notes. And then you have folders called day 1, 2, 3, 4, with the tutorials for the afternoon and all the input files that you will need with LAMPS and the other codes. So just for you to have an idea of where we are going. So today will mostly be basics on first crystallography, then crystalline defects, and then a brief overview of atomistic simulations, talking about interatomic potentials and molecular statics and dynamics. This is all to set the stage for this afternoon, where in the tutorial, so we'll see how we can install LAMPS on all of your laptops, but once this is done, there are some exercises, quick exercises about crystallography, and then start modeling some simple defects, vacancies and interstitials. So this is for today. Then tomorrow, so we're gonna talk, what I want to do is show you how to model crystalline defects using atomistics, but also using the elasticity theory, and also how to mix both. So tomorrow we're gonna start talking about basics in elasticity and on modeling one particular type of defect that I particularly like, which are dislocations. So these are part one of elasticity and dislocations. And then in the afternoon, we're gonna see how to model dislocations in practice. And then on day 3, it's the part 2 of the day 2. So we're gonna talk more about elasticity, more about how to model dislocations. And then here for that afternoon, I've prepared 3 different possible applications, and then you can choose the one you prefer or do more than one. Either look at a grain boundary or look at dislocations in oxide uranium, or use elasticity theory and eigenstrains, depending on what you want to do. Then on Thursday, we'll move to defect kinetics. Going to look at how we can model thermally activated processes. And then I have an example of an application of many of the concepts we will have talked about concerning solid solution strengthening. And then in the afternoon, we're going to look at defect kinetics and vacancy migration, and how to get the migration barrier of a vacancy. And then on the last day, so what I've written here is we're going to talk about multi-scale modeling. Actually, I haven't prepared anything for that last day because I don't know how the days before will go. So we'll see what we do on Friday. Maybe we'll talk about multi-scale modeling. Maybe we'll do more tutorials, depending. This will really depend on your interests and how far we've gone. So we're not going to do DFT here. It takes too much time, too much computing time. I want you to be able to run simulations on your laptops. So we're only going to do classical MD, and even with simple interatomic potentials. Otherwise, it takes too much time. Just as a show of hands, so who has already done, I don't know, atomistic simulations? 1, 2, 3, little bit, okay. Who knows what an eigenstrain is? 1? 2, maybe? Okay, who knows what I don't know, a dislocation is? Who has already seen dislocations? Okay. More, good. Okay, who has absolutely no idea about everything I just asked about? 1, 2, okay. 3, okay. So we'll see how it goes. Please ask questions if I'm not clear, right? I didn't know where to put the bar in terms of where to start and the difficulty. So please let me know if I go too fast or too slow. Just let me know, and I will try to adapt to that. Okay, that works. Okay, so that was just the introduction. I thought, and Ilaksh asked me to start with saying a few basic things about crystallography. So that's the aim of this first lecture. So we're going to talk about so notions of a unit cell, Bravais lattice, then crystallographic directions and planes, and then since we're going to model defects in different cubic systems, we're going to say a few words about the face-centered cubic lattice, then body-centered, and then we'll end with the hexagonal closed-pack lattice. So I guess you all know that a crystal is a solid where the atoms are arranged in an ordered and repeating pattern. And the repeating pattern is made by taking a unit cell that we periodically repeat in space in all 3 directions. And the vectors of that unit cell, so that would be this vector here, that vector, and the last one, the end of these vectors form the so-called Bravais lattice. Now, in a case like, for any crystal, there is a primitive unit cell, which is the smallest unit cell that we can build. And so for a simple cubic system like this, it would be just a simple cube here. If I take a face-centered system, then the primitive unit cell would be a cell like this one. We know from crystallography that this cell contains all the symmetries of the crystal, but the symmetries may not be that obvious to see in this unit cell. So usually, very often, instead of using the primitive unit cell, we use what we call the conventional unit cell. So for a system with a cubic symmetry, we use a conventional cubic unit cell that has more than one atom inside, but has the advantage of showing better what are the symmetries of the crystal. Okay, so these are, we're going to mostly talk about body-centered and face-centered cubic crystals, and these are their conventional cubic unit cells that we're going to play with during the week. Is that clear, or you know all of this? This is just very basic. Okay, good. So here, that was just to remind you that, so this would be the primitive cell, and these are the conventional cells. In the simple cubic lattice, we have 6 first neighbors. In the BCC lattice, we have 8 first neighbors and 12 in the FCC, and these are distances with the first neighbors. Nothing really interesting. This is just the Mendeleev table where, so I've put in reddish, these are the BCC crystals, in green the FCC, and then in gray the HCP. You see that, among the elementary elements, there's a fair distribution among the different structures. What is interesting is that there's only one simple cubic element, which is polonium here. And the reason is that in the simple cubic system, although I'm going to illustrate a lot of what I'm going to say with a simple cubic system, no elementary element is simple cubic except polonium. And the reason is that, and we can talk about it later, but here, this crystal is unstable with respect to shear here. The vertical interactions here are easily deformable in these directions, and that creates instability unless you have very strong angular interactions. Whereas here, with one extra atom in the middle, then you create interactions that are not vertical, and this stabilizes the crystal. So simple cubic, although all illustrations are with a simple cubic, are actually mostly unstable. Okay, now the Miller indices. I don't know if you've already, I guess many of you have already seen the Miller indices. The idea of so to define the Miller indices, we start with the Miller index of a plane. So Miller index or indices of a plane. So to get these Miller indices, what you do is you take the plane and you look at where the plane intersects the 3 axes. So if this is x, y, and here we have z, you get the coordinates of the intersection points along the 3 axes. So this could be, for example, I say 1/3, this could be 1/2, this could be 1. And then from the intersections, I take the inverse. So I have intersections. Oh, also, yes, if you cannot read me, sorry, can you read this, or is it hard it's okay for you? Okay. Sorry, it's a French way to write. So intersections with axis, and then you take the inverse. So for example, here the intersections would be 1/3, 1/2, and 1. And once I take the inverse, I get 3, 2, 1. And these are the Miller indices of that plane. Yes, it's clear for everyone? This is also basics. Now, if I take a crystal with, so any crystal has symmetries, and so if I have symmetries, then I have equivalent planes. So for example, what are the Miller indices of, so if this is x, y, and z, what are the Miller indices of this plane, for example? This is 1, 0, 0. And you have equivalent planes that would be what? What are the equivalent planes? You would have 0, 1, 0, which is this guy, 0, 0, 1, which is that guy. And so planes that are equivalent are noted with parentheses like this. So this would be the family of 1, 0, 0 planes. These are all the planes that are equivalent to 1, 0, 0 by symmetries. And then for planes, we use, you said it. So we would have 1, 0, 0, then we would have 0, 1, 0, then we have 0, 0, 1, and that's about it, right? Now, and this works, this is the mostly useful in cubic systems. The Miller index of a plane is also the coordinate of a vector, which is perpendicular to the plane. So we can also use Miller indices to index vectors. And vectors are noted with square brackets like this. So for example, 1, 0, 0 would be the x-axis. So that would be the vector 1, 0, 0. And same thing, we have symmetries between the different vectors. And all vectors that are symmetrical, that are obtained by symmetries, are written with these I don't know how to say these in English. These brackets here. So we have 1, 0, 0 would be all the. Yeah, that works for everyone. Yes. Sure. Okay, so this is what I wanted to say about the Miller indices, and this was just one example in. This would be a cubic system. So this would be the 1, 1, 0 plane, and you have the 1, 1, 0 direction here or here, the 1, 1, 1 plane, and the 1, 1, 1 direction there. And this is the 101. We've talked about it. Okay, so this was for the generalities. Now I want to say a few words about the FCC lattice. So you have the FCC conventional unit cell, which is here. Now the first question is, what are the Miller indices of the families of the smallest lattice vectors in this, for the FCC lattice? So it's a question for you. So FCC, I have atoms on the cube edge, on the summit of the cube, and then at the middle of every face. So I have one atom at the back here and another atom at the back there. So if Miller indices are clear, what are the Miller indices of the smallest lattice vectors in this half, 0? Do you all agree? So if this is x, if at the back this is y, and at the top here this is z, your colleague says 1/2, 1/2, and 0, so that would be a vector like this one. Do you all agree? Do you think there's a smaller vector than this one? No, right. So this is, so the smallest vector is so I will say 1/2 of 1, 1, 0. And by symmetry, this is what are the other possible vectors? Give me another shortest vector. We have all the cubic inversions, so we have 1, 0, 1, etc., etc. And this forms the family of 1/2 1, 1, 0 plane. So we would write it 1/2 of 1, 1, 0. Yes, that works. Okay. Now the second question was the Miller indices of the densest planes. in the crystal. So do you know what are the densest planes in the FCC lattice? It's 111, right? So 111 would be this guy here, for example. And then again, with the symmetries, we have this guy. We have someone who goes from here to the back, and et cetera, right? So this would be, so we have a plane 111, which is by symmetry equivalent to, then we do permutations with the numbers. So 1 minus 1, 1, and then 1, 1 minus 1, et cetera, et cetera. And this forms the family of the 111 planes that we write with parentheses like this. Yes, that works? So what's the, if I look at a dense plane, so a 111 plane, how are the atoms organized in that plane? Oops, sorry, yes, thank you. So if I look at a 111 plane, how are the atoms organized in that plane? It's hexagonal. Is it clear for everyone? Yeah. So if I look at let me take another color. If I look at, so I have one atom here. If I'm looking at this 111 plane, I have an atom here, one here, and then the plane contains the atom which is on the back face here, and then also here, right? And if I draw the triangle next to it, I have another atom here, and then I have an atom here, and this will form a hexagonal plane. So right, and then I have atoms. What's the lattice parameter of that hexagonal plane? What is the lattice parameter? A by root 2, right? That's what you said, yes. So exactly, so this vector here is a 1/2 of 110 type vector, and its length is a over square root of 2. Yes, that works? So show the equivalent 110 directions in a 111 plane. So I've already started. So this is a 110 vector, which in that plane could be this guy. But then we have also one which is here, and then we have the other one which would be here or which would be there, right? So we have 3 110 vectors that are like this and that are contained in the plane. Yes? What are the axes of an orthorhombic unit cell adapted to describe an FCC crystal seen along a 111 direction? So the question is a bit difficult, but so we were saying, so this is the cubic, this is a conventional cell with the cubic symmetry. If I wanted to define a unit cell which would be adapted to an FCC crystal with this orientation. So this orientation means that the direction perpendicular to the plane is what direction? So I have 111 in that direction, right? And then I have the 111 plane with that orientation. What kind of unit cell could I use? We'll take 3 perpendicular. We could take non-perpendicular, but that would be more complicated. So if we take 3 different perpendicular directions, what would we take? So we have so perpendicular to us would be 111. 110. And then, and I go from here to where to form a unit cell? To this one, right? So this would be my unit cell. Yeah, clear? If I take this one and I copy it, then I get this guy here. If I go down, I get this guy here. And so I recreate my hexagonal plane with this. And so the 3 directions, so x, which will be this vector here, will be along, so will be parallel to a 110 direction. Y will be parallel to this direction, and you said 1, 1, 2, which is correct. So this is a 1, 1, 2 type of direction, and then Z will be along 1, 1, 1. Yes? And how? Yeah, and then the big thing is for the FCC crystal to understand dislocations, we need to understand how these hexagonal planes are stacked on top of one another to recreate the FCC crystal. So do you know if so here I'm looking at one plane, which is this white plane here. The next 1, 1, 1 plane would contain this atom, that atom, that atom, and then I go down here. So I take this atom, that one, and that one, right? If I want to draw with that view, if I want to draw this new plane, so the next 1, 1, 1 plane, how do I do? Or where are the atoms placed in the second plane? The open gaps, so yes, so there are so in this plane, what is characteristic is that you have downward triangles like this, right? You have a series of downward triangles, and then you have a series of upward triangles, which would be this one, this one, this one, and this one, and etc. Right? So to form the next 1, 1, 1 plane, what I do is I place one atom at the center of either every downward triangle or every upward triangle, right? So if I start with the upward triangle, for example, it means that I would put an atom here, and then I have an atom here, and then I have an atom here, and then one here, etc. And I reform a second hexagonal plane, right? So that would be my second plane, and then the one after, what I do is I place the new atoms at the center of the either downward triangles of the very first plane or the upward triangles of the second plane, right? But it's easier to see from the first one. So now I put an atom at the center of every downward triangle. And that again forms another hexagonal plane. And then the next one. Then I go back to the first plane. And then I go back to the second, and then I go back to the third, and then back to the first. Actually, I follow this line here. So, yes, this one. First plane, second plane, third plane, and then I'm back to et cetera, et cetera. So I can define three types of plane that we usually call, this would be a type A plane. The blue one would be a type B plane. And the orange one would be a type C plane. And so the stacking is, as is well known, the stacking is a ternary, and it's of the type A, B, C, etc., right? So ternary stacking. Everything's clear? Yes? So if I do this ternary stacking, I create a perfect FCC crystal. Now, what happens in practice is that sometimes there are defects in this stacking. There can be either a missing plane or an extra plane. And these are called stacking faults. So there are two types of stacking faults. Let me erase this. So let me start by saying, so A, B, C, and A. And let's assume that the stacking is okay up to here. So it means that here I have A, B, C, and here I have A, B, C. And now here, let's assume that I don't get the A plane that I was expecting, but I'm missing a plane. So instead of having A, I get directly to B. So I have B, and then I have then the stacking is again okay. So the B is here, the C is here, and then I have an A, and then I have a B, etc., etc. So for those who have already know all of this, so do you know how this? So this is a stacking fault because there's a fault in the stacking, and it has a more specific name. Do you know? Does someone know how it's called? Yes, it's called an intrinsic stacking fault. And what is special about this intrinsic stacking fault? It's locally, the stacking is, if I look locally around the fault here, the stacking is not ternary, but it's binary, and the binary stacking is characteristic of what crystalline structure? HCP. So what we always say is that the intrinsic stacking fault forms locally an HCP stacking, right? So this would be, yeah, anyway, it's on the slide, but this is intrinsic. Now this one, what am I going to do for this one? So I'm going to say, so if I have an extra plane, it's going to be called if it's not intrinsic, it's extrinsic. And so what plane am I going to put here? So I got everything. I got A, B, and C. So you got to make up your mind, guys. So if it's A, then it's not a stacking fault because it's the A here, right? If it is C, then I put C atoms on C atoms. So I put two hexagonal planes exactly on top of one another, and that the FCC structure, the FCC interactions, they don't like to have these atoms on one on the other. So the only possibility is B. Right? That's the only one I can do. And then the next plane will be actually no. From here, what we do is we start again exactly the normal stacking, the stacking that we expect. So on top would be after B, it's C, and then I have A, and then it continues. What did I do? Wait a minute. No, it's okay. It's okay. It's that, yes. What is specific about that fault, which you don't have? What did I do? Say, I did something. Sorry. If I put an extra plane in between. Oh, no, yeah. Sorry. Yeah. My bad. Sorry. We do again. Sorry. So I have A, B, C, and then between these two, I want to add a plane. Sorry. So I want to add a plane between these two planes. So this would be, so between A and C, I can only put B. So I have B. Sorry. I put B in between these two, and then I restart the stacking as it was. So then I have A, B, C, A. Sorry. Yes. That should be better because now. So what is special about that stacking? So is it a binary stacking as before? No, it's not. What is special about it? What kind of symmetry do you see in this stacking? Yeah. Look at so if I take this plane as a reference, then on both sides I have B, and then after B on both sides I have A and so on. So here, so this was a binary stacking. This is not binary, but here I have a mirror. I have a local mirror plane, right? So here, if I take this one and I take this plane as a reference here, I have a local mirror stacking, C, and then I have B and B, A, and then not anymore. A symmetrical stacking like this, especially in an FCC metal, how is it called? It's a twin. So extrinsic stacking creates locally a nano twin. Intrinsic stacking locally creates a nano HCP crystal. Does that make sense? So this is locally HCP, and this one is locally twin.
How does extrinsic stacking fault form in
In real materials, so for example, in irradiations, where we're going to talk about a bit more about irradiation later on, but you create a lot of interstitials and vacancies. When the interstitials collapse to form a dislocation loop, they can form this extrinsic plane. Do you have questions? No, everything is clear? So let's see if I forgot something. So here you have the answer of the questions, but I think we got all the questions correct. And then we have, so I made nice animations to show, so the ternary stacking, and also, yeah, I didn't say, but so this atom here, we place it on top of the center of the triangle, but the height of the atom is such that these 4 atoms here form a perfect tetrahedron, right? So I have the 3 blue atoms here. The red one is on top, and then at a height such that this is a perfect tetrahedron. Yes?
I have a question. Do these faults have the same energy, or energetically they are different?
They are very different, yes. This one costs a lot more energy than that one. And yeah, this one you rarely see it unless in irradiation cases. This one you see it everywhere. Do you have? Yeah, it's clear. Yeah. So yes.
Why is it having more energy than the normal?
So the why, it's going to be difficult for me. I don't know. I can give you a quick, direct answer, right? But clearly, when you look at where the neighbors are, this one. No, actually, I'm not sure. I prefer not to answer. I'm not sure. I don't have any simple answer for you for that. I was about to say, but I would need to think more. I haven't thought about that for a long time. I think if you count the number of bonds that are well placed in one case and in the other, there are more bonds here. The change with respect to a perfect stacking is smaller here than here when you look at from one atom where its neighbors are. But I'm not sure. I would need to think about it to be sure. Are there other questions? No, it's okay. Okay. What did I want to say? Yes, in this triangle, so if I take a vector like this, what type of vector is that? Half 110, yes. This one, same. What about this one? Zero. Yeah. I have a half 111 and I have a 011. Half this one at the back here, half 111.
1 by 3 1.
So if it is 1 by 3 111, the horizontal plane is a 111 plane. So if it is a 111 vector, then it is perpendicular to the plane. Is it perpendicular? No. So what vector is that? What type of vector? It's another 110 vector actually. So this vector is by symmetry equivalent to that vector, that one, that one. Same thing here, this is a 110 vector, and that's another 110. Actually, the 6 edges here show you the 6 possible 110 vectors of the lattice. And now this triangle here is along a 111 plane. this triangle here is also along a 1, 1, 1 plane. Same for that face, same for the back face. And actually, the 4 faces show you the 4 possible 1, 1, 1 planes of the crystal. Now, a vector going from the center of the triangle to the top atom here, this is a 1, 1, 1 vector, or a third of 1, 1, 1 going from here to here. And the 1, 1, 2 vector, where's the, if you showed me a 1, 1, 2. Yes, can you be more precise? If I take a 1 triangle like this, right, this is the bottom triangle, for example, and if I want to draw a 1, 1, 2 direction,
Center of the atomic position to the edge center.
So I know that, what did we say? We said that when we built the unit cell here, we said that the 112 was perpendicular to the 110. So if this is a 110, I know that 112 will be perpendicular to it. One way to draw it is from the center, I take one edge and I go down to the center. This is a 112 plane. So this is 110, this is 112. And then how many 112 vectors do I have? I have 3, right? I have this one, that one, and that one. Yes? Is it clear? Yeah? So we're going to come back to it when we talk about dislocations in FCC crystals, but this tetrahedron is called does someone know the name? The Thomson tetrahedron. And it's very useful because it shows you all the 110 vectors, all the 1111 planes, and all the 112 vectors that are the partial dislocation vectors that we're going to talk about later on. And this is my animation for the stackings with the mirror planes and etc. Okay. What about the BCC lattice now? So we do the same game. Miller indices of the smallest vectors. So to form a BCC lattice, or the conventional BCC unit cell, I have atoms on the corners, and then I have one atom which is in the middle of the cell. So yeah, it's always hard to show it, but it's hidden here. One in the center, and then one at every summit. So what are the smallest lattice vectors? It's half 111, right? So this is here, half 111. And how many do I have? 4 different, right? The Miller indices of the densest planes. 110. So a 110 plane is, for example, this guy here. Right? This is a 110 plane, and these are the densest planes. What's the crystalline structure of a, oh no, I wanted to say 110, sorry. It's not 111 here. That's a typo when no, wait a minute. No, it's correct. No, it's 111 I wanted to say, sorry. So this is a 110. Now, if I look at a 111 plane, so that would be a plane like this, right? This is 111. If I look at the crystalline structure in that plane, what does it look like? So actually, there are 3. Actually, this one here, it doesn't. No, you're right. Sorry. So you have 3 here, but then if I look at the neighbors, what will that form? You'll have a triangle. Here you have an upward triangle. If I look at the atoms nearby, that will form a downward triangle, and etc., etc. So in the end, the plane is hexagonal. Again, right? It's still a hexagonal plane. If I look at the plane above, what's the crystalline structure of the plane above? Or, sorry, if I look at the next 111 plane, it's also going to be a hexagonal plane, right? There's no reason why it would not. if I wanted to place it, if I wanted to make the stacking with this one, what would I do to make to place the hexagonal plane? I would do exactly the same as the FCC, except that. So you're right. So the next plane is also a hexagonal plane. So I will put it at the top, above the center of all the upward triangles, for example. That's FCC, right? So no, what's the difference? Why is this BCC and before it was FCC? What would be the difference? Bottom three atoms. True, yes, they are further apart, but with crystallography, we don't really care about do the atoms touch or not. We only look at the center, the positions of the centers of the atoms. So that's not the distance is not enough to make a difference.
Only two atomic planes will be there, like A and B.
Actually, no. It's an ABC stacking. The next plane will be at the center of this one to above, so it would be here. If I only draw that, then you cannot make a difference between FCC and BCC. So what's the difference? Because this is not FCC. What will be? Yeah. Exactly. So here we're going to form again. We form tetrahedra. Here, right? Here I have a tetrahedron here, but it's not a perfect tetrahedron. The height is smaller than in FCC, and so I think it's. I have a drawing here. So the stacking is ternary, but then if I have the three blue atoms that form a triangle, I have the red atom on top. The length of this vector here is not the same as the length of that vector. So in both cases, it's tetrahedra, but here it's not perfect, whereas in FCC it's perfect. That's the only difference between the two stacking. Is that clear? Yes? And now we have the bad guy. We have the crystal where everything fails or everything. So FCC, it's the good guys. FCC, everything is fine, clear, etc. BCC, it's in between. HCP is clearly the bad guy in the story. So here, so to form an HCP crystal, we do again we stack hexagonal planes, but this time, as we said before, with a binary stacking: AB, 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 AB. Right. So this would be a typical HCP crystal. When we look at Miller indices, actually, if we look at the usual Miller indices, the planes that are equivalent from symmetry do not have equivalent Miller indices, just a permutation of the Miller indices. If I use the usual 3 Miller indices, because I will have one vector. If I use the usual one, I have one vector which would be, for example, this vector, and the other one is that one in the horizontal plane. These two vectors are not equivalent, and so when I do a permutation of the Miller indices, I do not get an equivalent plane. So to restore the symmetries, we use not 3 but 4 Miller indices that are obtained by the intersection of the planes with the 3 equivalent hexagonal vectors here, A1, A2, A3, plus the c-axis. If we use these 4 vectors, then equivalent planes are equivalent by permutation of their Miller indices. And since the 3 vectors here, they are not independent, I mean, they're not perpendicular one to the other, then the Miller indices, the 3 Miller indices that we get from these 3 are not equivalent either. And there's a simple relation. So we have 4 Miller indices, but then the third one is always minus the sum of the first 2 vectors. So here, so this was BCC. Or do you have questions about the BCC lattice, or everything was clear? At that stage, it's clear? Okay. So now HCP. So let me try to draw that on the board. So I have A1, which is here. A2 is here. A3 is at the back here. And then I have the C-axis here. So for example, what are the Miller indices of, so let's start easy, the plane which is at the bottom here. So I have a 0, 0, 0, 1. I have a 1, 1, 0. I'm not sure you finished. 1, 1, minus 2, 0. So who's, if I did a woo clap, if we do a woo clap, hand woo clap, who thinks it's 0, 0, 0, 1? Okay, who thinks it is 1, 1, minus 2, 0? Okay, so there are many people who are really not sure of them, and then no one is backing you up. I'm sorry, they're correct. I mean, the correct answer is 0, 0, 0, 1, right? Because the plane here, to do the Miller indices, I should not take a plane that goes through the origin, right? I need to take a plane that is here. So if I look at where that plane intersects the axis, it intersects, so A1, A2, A3, it does not intersect them because it's parallel. So the intersection would be infinity, 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 and then the C-axis, it crosses it at 1. So if I take the inverse of that, so the inverse would be 0, 0, 0, 1. So that's this blue plane here, and how is it called? What is its name? That's the basal plane. Okay. Now, let's take this plane, for example. So how is it called? So what's its name? Prismatic plane. Okay. So where does it intercept the different axes? We'll do it step by step. So A1, it intercepts in 1, yes. A2, infinity. A3, minus 1. And C, infinity. Right? So if I take the Miller indices, it's going to be 1, 0, minus 1, 0. Am I right? 1, 0, minus 1, 0, yes.
That should be curly bracket. Because we are drawing for the plane. So if we are including that 0, 0.
You mean this? This is, yeah, you're right. Sorry. Thank you.
Sir, is this choice of the necessity of including one more indices to make it symmetric, is this coming because of bad choice of the unit cell? I mean, the conventional cell?
Yes. The main issue is that the conventional unit cell would be this vector, that vector, and then the C vector. And in that unit cell, this vector is not equivalent to that vector. These are not the same vectors. And so when you look at the Miller indices with these vectors, the way the planes intersect either that vector and that vector, if you do a permutation of these numbers, you don't get the same plane. Whereas here, the three A planes here, they are equivalent by symmetry, by the threefold symmetry of the crystal. And so when you do the symmetries, you get equivalent planes. So the fourth one is C will always be different from the others. Yes. Yeah. So for example, if I do a permutation, permutation between these three. So if I do, I do 0, 1 minus 1, and 0. Yes, I see your question. The permutation does not include this guy. It's permutation between the three first, not this one. So this plane, so who is this plane? If I know how to get it, yes. This one? Yeah, it's this one. It's this one, right? So this is the basal plane. Prismatic plane, or prism plane, which is what would you mean? 1, 0, minus 1, 0. And now we have the pyramidal planes. So the first, so we have the first pyramidal plane of first kind, which is this one. What are the Miller indices of this pyramidal one plane? Wow, you're too fast for me. So say it again. You said what? 1, 0, 1 bar, 1. So 1, 0, 1 bar, 1 bar, 1. Yes. Is it 1, 0, 1 bar, 1? Yes. So that's called pyramidal 1. Yes. This is. And then we have the pyramidal 2 planes. Do I need another color. I need green. And so the pyramidal 2, it's this one and this one. Do you see what I drew? So I take these two and those two, and this one, if I look at the intersections, so it intersects A1 at half, A2, it intersects at minus 2. No. Yeah, it's 1. What did I know I drew something. Yeah, it's because my drawing is crude. This point here should be aligned with this point here. This should be on the same line. I'm sorry, yeah, my drawing on the board is crude, right? So this is minus 1, actually. You agree? Yeah, I'm sorry, yeah, you see. So this is minus 1. And then A3, it's also minus 1. And then C, so it's maybe hard to see, but it's 1/2. So the plane is, I take the inverse, and so 2, 1 bar, 1 bar, 2. And I hope it's correct. 1, 1 minus 2, 2, yes. That works? Yes? And we have this one is equal to, so I do 2 minus 1, this is 1, I take minus and I get minus 1, so I'm correct. So these are some examples I added just as an exercise. And that's what I wanted to say about crystallography. Do you have questions? No. So it's true only if you have a cubic primitive cell. So the you need to have 3 orthogonal axes with the same length. If it is orthorhombic, so if it is perpendicular but not the same length, then the vector that you have is not perpendicular in the Cartesian sense. It's perpendicular within the basis, but not within a Cartesian space. It works only if you are cubic. And so here it's not true at all. If you go to very high Miller indices, Then for a small change in the Miller index, you can have also a change in the density. So you could do a continuum approximation, a continuous approximation towards zero density, which I don't think we ever do, or I don't know, maybe people do it. I don't know. The physical density in terms of atoms per meter cube will definitely depend on the C/A ratio. But then the density in a plane in terms of number of atoms per lattice parameter, for example, may or may not depend on the C/A ratio. No, it will depend on the C/A ratio. Yes, you're right. Yes, yes. No, you're right. Yeah, it will depend on the C/A ratio. So in practice, actually, planar defects, there are few planar defects, and they are mostly along the dense planes. You don't have an infinite number of stacking defects. In practice, no. In practice, there are only very few stacking defects. So actually, just for dislocations, for example, people will mostly look at basal and prismatic, but also pyramidal 1 and pyramidal 2. And also, so we can talk about that more later on, but we know that we don't have enough slip systems or dislocations to accommodate any type of deformation, plastic deformation in an HCP crystal. So you often also need twinning. And so you also have the twinning planes that come in that are also important in that guy. So bad guy, everything is... In FCC, basically 99% of everything happens on the 111 planes. Here, everything is all over the place.